Okay, Bismillahirrahmanirrahim. So, insyaAllah we will continue our first topic, first chapter, Introduction to Machinery Principle. Okay, so before that, what videos. Boleh nampak?
Boleh nampak? Boleh.
Lambat sikit.
Toyota knows how to make cars. It does it so well, it became the first company to produce more than 10 million a year. Its success is rooted in a special system and began what's now known as lean manufacturing, an ethos emulated by companies around the world to make products faster, cheaper and better. Here's how Toyota changed the way we make things. Following the Second World War, Japan was left in a precarious economic position.
Steel and other metals are scarce.
Already disadvantaged by lacking natural resources, materials were hard to come by, and companies had to be creative to compete. Toyota's founder, Seiichi Toyoda, had started a loom business, but it was his son Kiichiro who founded the motor company in 1937. They were used to working within narrow margins. As the shortage of materials increased during the war, the number of headlamps on its Model K truck was reduced to one, and it only had brakes on one of the axles. The turning point for Toyota's production system would come in the early 50s, when Kiichiro's cousin Eiji would travel to the US with a veteran loom machinist, Taiichi Ono. They visited Ford's River Rouge plant in Michigan, and were impressed by the scale of the operation, but knew that in cash-strapped Japan, companies didn't have the resources for such a system. Having months' worth of stock sitting in a warehouse would tie up precious capital they didn't have. Instead, what truly impressed Ono was a visit to a supermarket, a Piggly Wiggly, according to legend. Japan didn't really have self-service stores at this point, and he was struck by the way customers could choose exactly what they wanted, when they wanted. He decided to model his production line on a similar idea. With the supermarket formula, only enough parts were produced in the first phase to replace what was used in the second, and so on. This is where the just-in-time system really took shape. Toyota was able to eliminate much of the waste in Ford's system, making smaller numbers of parts to be used when it needed them, allowing the company to operate on a tighter budget. As part of this, Ono developed Kanban, a sign-based scheduling method which shows goods in production, and goods out. It's now seen as a precursor to barcodes. Ono and Toyota also noticed that American car companies were still employing many of Henry Ford's early production techniques. They kept operations at full tilt in order to maximise efficiencies of scale, but then had to repair defective cars after they rolled off the line. Ono believed this caused more problems and didn't encourage workers or machines to stop making the mistake. So he placed a cord above every station which any worker could pull to stop the entire assembly if they spotted a problem. The whole team would work on it to prevent it from happening again. As teams identified more problems, the number of errors began to drop dramatically. Combined with a culture of continuous incremental improvement called Kaizen, the Toyota production system built a brand known for making reliable and affordable cars. But Toyota was also getting good at producing cars quickly. In 1962, the company had produced 1 million vehicles. By 1972, they'd produced 10 million. It was around that time that the efficiencies of their factories enabled Toyota to produce a car every 1.6 man-hours, much lower than their competitors in the US, Sweden and Germany. And as the oil crises of the decade sent gas prices higher, cheap-to-run Japanese cars became much more appealing to Americans, whose powerful but gas-guzzling vehicles suddenly became very expensive to run. Today, Toyota has made over 250 million vehicles. Others have looked to them to learn the lessons of lean, combining craft with mass production, avoiding waste while striving for constant improvement. Boeing is perhaps the most famous, restructuring a plant to better suit TPS. Intel is another long-time Lean ambassador and is exploring the principles in the context of AI and the Internet of Things. A Canadian hospital even used Toyota's system to decrease wait times in its ER. The Toyota production system changed not just how cars are made globally, but how we approach making things full stop. It also showed that there's always a better way to make a product.
Okay, so you can see the main word they use is lean. Okay, so mean that improvement. Okay, so you boleh tengok where when they have a problem, they try to solve it and improve it. Solve, improve. Okay, because problem keep on happen. So you cannot run from the problem. You try to face and fix it and improve it. Okay, so that I really hope also you can take some motivation on the workplace area, okay, for your future. Okay, ready? So we have 43, I think 42, 43 students. I'm recording. You also can record, don't worry. Okay. Bismillahirrahmanirrahim. So we are continue with our lesson, which is the magnetic field. Okay. So this is a basic or the main element in the electrical machine, where it's the very fundamental mechanism. Okay. Yeah. From as we know that an electrical machine is converted from one form of energy to another form. Okay. Then we have a electrical machine. They can be explained in 4 general principles. Okay, the first one is electromagnetic action. Okay, so how the magnetic magnetic action is induced. Okay, it's by a current carrying wire. Okay, when there is a wire and current flow through it. So and then the magnetic field will appear around it. Okay, the magnetic field is around it, around the wire. Okay, and then the second one is a transformer action. Okay, transformer is like a play around with a time changing magnetic field. Okay, so which is a magnetic field is continuously run. Okay, go through pass through the core. Okay, they call it a time changing magnetic field, induce a voltage in a coil of wire in pass through that coil. Okay, it's like if I'm not mistaken, it's a Faraday's law. When you have a coil and then you move the magnet. So if you move only once, the voltage will induce from 0 to high and then go back to 0 again. Okay, because there is not continuous movement. It's not a time changing. It's just a one time only. Okay. So transformer action is like you are moving it quickly, something like that. So the voltage will always induce. And then the third one is the motor action. Okay, so motor, we know that when we apply a current, so the current will pass through the coil and the coil will induce the magnetic field. Magnetic field will interact with the permanent magnet. So the force will be action. Okay, there will be a force action. Okay. And then the last one is the generator action. Okay, it's a moving wire. Okay, instead of you move the coil, instead of you apply a current, now you are moving the coil. Okay, you are moving the coil in the presence of the magnetic field, and then the voltage will be induced. Okay. So yeah, sometime during the exam, they can ask you what is the 4 general principle. Okay, so you can write the main thing: electromagnetic action, transformer action, motor action, and generator action. Okay. Okay, so for the magnetic field, how we want to know the direction? Okay, so direction. This direction is only for the current carrying wire carrying current. So when there is a wire, okay, wire, and then the current pass through it, okay, just use the Ampere's right hand rule, okay, because yeah, we have another hand rule after this, right hand rule, left hand rule, okay, but it's different, okay. So this is, I think, the most simplest one and the most easiest, okay. How you want to know the direction of wire, just use your thumb, okay, right hand, okay, and thumb and finger. So your thumb is the current flow, and the finger is the magnetic field. So this is wire. Tak nampak. Okay, this is wire. Then this is the direction. So direction is the wire, the current flow upward. Okay, something like that. Okay, and this is the symbol for the current go into, okay, into the paper, and this one is come out from the paper. Okay, you boleh play around with your finger over here, right hand rule. Okay, so this is a magnetic field for this one around the globe. Okay, so we have a north pole. So north pole over here, this one, yeah, when we say this is a north pole, okay, but this here is like a south, and this is like a inside is like a north, because the magnetic field come out from the north, okay. And when you have a compass, okay, we are at the surface of the earth, the compass will show you that the north is upward and the south is like this. So they will show you like this, compass, okay. Compass akan show macam ni lah. Dekat dalam dia akan terbalik. Bila dia masuk, dia come out from the north and then go into the south, okay. So that's why they call it as a north pole and south pole macam ni, south pole. So yeah, the line they call it a flux line, flux line. Okay. So okay, so this is the famous rule, the famous hand rule that we are using. We will be using it for our entire course, which is the Fleming's rules. Okay, we have a left hand rule and right hand rule. Okay, for the right hand for the generator, okay, generator, and left hand for the motor action. When this is a current supply, for generator is current is generated. Okay, both have the same symbol. So if you want to remember, easy, FBI. Okay, FBI. The sequence is FBI. Jangan terbalik. Okay, so F is the force, B is the magnetic field, and I is the current. Okay, same to the right hand rule. Right. Okay, so both the thumb is force, finger is the magnetic field, and the middle finger is the current. Okay, so cuma terbalik, so jangan you confuse. So hopefully you can clarify it first. Okay, so right hand for generator, left hand for motor. Okay, so now this one is like quite similar with the transformer. Okay, so this is the basic. So basic, the production of magnetic field. Okay, so when we go to fundamental, so the action come from the Ampere's law. Okay, where the H actually is the magnetic field intensity. Okay, magnetic field intensity, we integrate it. Okay, we integrate it to the length. Okay, this is length, differential element of mean path length. Okay, so how what you understand by the integration? So last week we see that when the H, okay, when the H intensity is constant, the equation will become like this, like only multiplication, multiplication only. Okay, so ni kalau constant, kalau H is constant. Okay, so if not, it's like a summation, so it's like a summation, H1 L1 plus H2 L2 plus H3 L3. Okay, this is what integration mean, because they have a specific intensity at a specific length. Okay, the intensity is different, okay, for the each length. So if constant, just directly like this. Okay, okay, the total the integration will be equal to the I net, okay, the current, okay. Okay, you can see that essentially all the magnetic field produced by the current will remain, okay, will remain inside the core, so that the path of integration in Ampere's law is that the mean path length. Okay, so actually this is an assumption. Okay, the assumption mentioned that the magnetic field produced by the current will be remain. Okay, there will be no leakage. Okay, so this is the assumption. Okay, so when they say when they assume like this, so then they assume the length. Okay, the length will be taken from the center. Okay, center of the core, from the center, not from outside, not from inside. So from the center, from the center of the core. Okay, so that is, they call it as a LC. Okay, so the current passing within the path integration is I net, so it then become Ni. Okay, because there is a several turns. Okay, since the coil of the current, the wire cut to the path of integration n times, so while carrying I, Ampere's law does become, so actually from here the I net become Ni. Okay, so I is come from the supply current, and there is a few number of turns. Okay, so this one assume the assumption become H is constant. They assume that the H is constant. Okay, so that become like this. Okay, if only one turn, there will be like this. HL equal to I. Okay, because only one turn. Okay, so since there's a n turn, they just add Ni. Okay. So then we rearrange. We rearrange the equation. So just focus on the H. Okay. So the H is called the magnetic field intensity vector. Okay. Actually, the H is a sense of measure of the effort that current is putting into the establishment of the magnetic field. Okay. It's like the effort. What is the effort of the current? Okay. They call it a magnetic field intensity. Okay. So then, how about this flux? So this symbol is flux. Okay. These are the flux. They call it as a flux. So the strength of the magnetic flux produced in the core also depend on the material. Okay. So it depends on the material. Either is steel. Okay. Sometimes the material is steel, and then maybe iron, or apa lagi? Aluminium. Maybe others. Okay. There are a lot of materials. Okay. Then the production of flux, okay, will be based on the magnetic field intensity and also the density. Okay, so don't get confused. Okay, because the relationship between the magnetic field intensity, so this is intensity, the H, and the resulting magnetic flux density, okay, produced within the material given by, so B is equal to mu H. Okay, so the flux will come after this. Okay, we will measure after this. So before to the flux, we must measure the density first. Okay, magnetic flux density. Okay, so this is the relationship. Okay, So the B, they call it as a magnetic flux density. The unit is Tesla or Weber per meter square. And the mu is the magnetic field, magnetic permeability of the material. Okay, the unit is the Henry per meter. And then the magnetic field intensity, the H. Okay, the unit is ampere turn per meter. Okay. Okay, so then the mu, okay, this is the magnetic permeability. Okay, the permeability of any other material compared to the permeability of the free space. So each material, they have their own constant. Okay, the permeability, the mu, they have their own scale. Okay, so then we call it as a relative permeability, where we compare the material, the material mu, the mu of the material compared to the free space. Okay, free space of permeability. Okay, so we get as the mu r. Okay, so most of the students confused with this equation. Okay, so during the exam, most of the students they just directly calculate, become like this, B equal to mu r h. Okay, they just directly use. Okay, so somehow in the question they give you mr, they give you mu r. Okay, in the exam they will give you mu r. Okay, they're not giving you directly mu, they give you mu r. Okay, relative permeability. So you need to measure first. Okay, you need to calculate it first. So you need to get mu first. So mu equal to mu naught. Okay, you need to measure. You need to calculate mu r, mu naught. Okay, so from here, once you calculate that, then you can use the equation. Okay, so this is become only mu. Okay, so please don't get confused. So the mu naught of the free space is 4 pi times 10 power of negative 7 Henry per meter. Okay, then we have a magnetic field intensity, we have a magnetic field density, and then we try to replace. Okay, we try to replace the H. Okay, where we know that the H is equal to Ni over L, LC. Okay, we try to replace. Okay, so we replace the H. Okay, then they become like this: mu Ni over LC. Okay, and then what is the flux, the total flux? Okay, the magnetic flux or the total flux. Okay, sometimes they call it only flux. Okay, it's in a given area. So flux, the calculation of the flux will depend on the area. Okay, so the flux is equal to the integration of magnetic field density with the differential of area. Okay, so this one means that the area is not constant. Okay, not constant. Okay, they have several area. Okay, several area through the to the core. Okay, if constant, okay, they just only a multiplication. Right? Okay, if the magnetic density vector, okay, the direction is perpendicular to a plane of the area. So macam ni lah. Contohnya the core. So this is the core. Core. Okay. So we just take this point. Kita ambil sini je. Then kita keluarkan. So tak payah keluarkan lah. So flux tu lalu kan, lalu macam ni kan. So dia perpendicular. So nampak tak dia perpendicular? So this is area. So yang ni adalah flux. So dia macam ni lah. Okay, so it become perpendicular. This is B vector. And this is the area. Okay, so this is what they mean. Okay, and if the flux density is constant, okay, throughout the area, so only it's just a multiplication. Okay, so in this study, we only focus. We will have several different area, okay, different area, and then we just need to like summation, no need to do integration, okay. For example, like this one, this is a BA1 B1A plus B2A, something like that, okay. Okay, so ni tak ada lah, dia macam ni lah, total dia akan jadi flux lah, okay. Ini kalau semua sama lah, if the material, the area constant throughout the core. Okay, so we have the equation for H, we have equation for B, and we have equation for flux. So we can combine it all together. Okay, so we have flux equal to BA. So B is this one. Okay, B you have this one. Okay, and we can replace it. Okay, so we try to rearrange. Okay, mu and I, A divided by LC. Okay, so yeah, this is the flux. So you need to just play around with the equation. Okay, sometime in the exam we give you for example the value of A, and then you need to calculate LC, for example lah. Okay, we can try to exchange it. Okay, maybe in the tutorial or the example we give you the LC, you need to find the A. Okay, and then in the exam you can try to rotate it. Okay, okay, so yeah, magnetic circuit, we can compare it to the electric circuit. Okay, so yeah, in the electric circuit we have a voltage, we have current, and we have the resistor, and then we use the Ohm's law where V equal to IR. Okay, so in the magnetic circuit, the voltage is called the magnetomotive force. Okay, where the symbol is like F, macam F lah macam ni. Okay, and we can also simplify it by using the MMF. Okay, MMF. So the value is ampere turn. Okay. How to get the unit? First, the magnetic force MMF equal to NI. Okay, so turn is the N, the current is ampere, so ampere turn. Okay. And then the resistor in the magnetic circuit, they call it as a reluctance. Okay, reluctance of the circuit. Okay, the symbol is quite similar with the resistor in the electric circuit. They use like a R. Okay, I think you can just write R only, no problem. Okay, and then we have a MMF, then we have a flux. So flux is like a current in the electric circuit, and reluctance is like a resistor. Okay, so we use the Ohm's law. Okay, so Ohm's law, we have V equal to IR. So for the magnetic circuit, we have the F equal to flux R. Okay, you can say like this. Okay, and then the flux is equal to F R. Okay, so now we have everything over here. So from this equation, okay, so from this equation, how to know that what is the R or the reluctance? Okay, okay, the reluctance is come from, so this is the equation, the BA. Firstly, BA, okay, flux is equal to BA, and then we replace the B. Okay, they will become like this. Okay, and then we take off the NI. Okay, the NI will be the F or the MMF. Okay, NI become the MMF. Okay, so the flux. Okay, of the flux, dia punya F. Okay, and then so we know that the flux is F over R. So we have F, and the other is 1 over R. Okay, this one is 1 over R. Okay, so this is 1 over R. Okay, if this is 1 over R, and what is R? Okay, so you just terbalikkan je lah. Okay, So the R will be like the R will be equal to LC divided by mu A. Okay, remember the mu not a mu R, not a mu naught, just mu. Okay, where the mu is equal to mu R times mu naught. Okay. So now we know already the force, the flux, the reluctance. Okay, so we know each other now. Okay, so yeah, so in the electric circuit, so we have in series and we have also the parallel. The calculation is the same. Okay, calculation is the same. So kalau series, just add on. Okay, if parallel, you have to do like this. Okay, 1 over R, 1 over R, 1 over R. 1 over R equal to 1 over R plus 1 over R plus 1 over 3 plus dot 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 dot. Okay. Okay, so this is the example of the core with the coil and current. Okay, so in order to know the direction of the flux, okay, you can use your right hand rule. So this one is a bit different. Okay, so there is a coil. Okay, so near the coil. So the coil, and then the coil is starting like this. Okay, starting like this. So this is become your finger. Okay, you finger like this, and your thumb will be showing upward. Okay, macam you genggam dia, you grab. Okay, it's like you grab. Okay, you grab the. Okay, tapi kena tengok you need to see the coil. So if the coil is starting like this, so from behind, okay, from behind. Okay, so from behind, for example, this. So you need to do like this Okay, boleh faham tak ni? You need to do like this. So macam ni kan? So this dia terbalik Ni thumb. Lukis tak kerti. Okay, so this is finger. Okay, so flux will be showing the direction of the flux is downward. Okay, so this one you need to see the grab coming from this side first. Okay, so you grip the core, then they show you the direction of the flux. Okay, and of course this one will become like this positive, negative. Okay, boleh faham tak? Can you understand until now?
Doctor,
Yes.
the term, is it the electrical force or just force?
The thumb, okay, the thumb is the flux. Okay, where the fingers is the direction of the current.
I see, okay.
Boleh faham tak?
Nampak.
So sebenarnya nak tunjukkan je direction dia, sebab coil tu, okay, this coil, sometimes dia lilit melalui atas, sometimes dia lilit melalui belakang. Macam ni macam bawah ni kan. Okay, so ni dia dah show you current flow to this. So kalau flow tu bawah ni macam mana? So kalau current flow from here kan, so you kena daripada bawah tu, you kena daripada belakang. Okay, so dia punya to show downward Okay, so ini kalau daripada sini. Okay, apa, nanti you balik, you boleh tengok balik lah. Okay, so now saya nak tanya you beberapa soalan satu soalan je lah sebenarnya. Okay, what are the reason for the inherent inaccuracy in the magnetic flux calculation? Siapa boleh jawab? Anyone can answer?
Current dia lari-lari dekat sepanjang wayar tu. Boleh ke?
Current tu lari-lari Okay. Okay, tak tepat lah. Okay, so yalah, kalau kita tengok there are several reason
Calculation dia mungkin dapat error, Doktor.
Yeah, calculation dapat error. Why? Because of what? Sebab tu dia tanya kenapa inaccuracy tu. Kenapa dia banyak ada ni? Sebab tadi pun saya dah sebut dia ada dia punya calculation tu based on the assumption. Okay, so itu one of the reason lah. They assume that the flux is remain inside the core. There is no leakage. Okay, and then the calculation of the mean path length, they assume that they calculate from the center of the core. Okay, so maybe the calculation take at the center maybe not accurate. Okay, tu one of the reason juga lah. Okay, so ni ada dia punya jawapan lah kat sini Okay, as I said, there are always the assumption or the approximation. So the reason of inherent accuracy, first is because the assume that the all flux is confined. Okay, there's no leakage. Okay, and then the calculation of the mean path length and the cross section area. Okay, because sometimes at the corner of the core, the calculation of course will be different. Okay, but they still use the same to others. Okay, and then the permeability varies with the amount of the flux already inside in the material. So there is inherent flux. Okay, and then when there is an air gap, okay, so if there is air gap inside the flux, okay, the effective cross section area, okay, for this one you can see from here there is air gap. Okay, air gap between the core. So the air gap cross section area, the area will be more bigger. Okay, so this is called due to the fringing effect. For example, this one, so this is the area. Kita ambil sini. Okay, ni contoh lah, ni area dia kan. Tapi untuk yang air gap, for the air gap, the area will be bigger. Okay, the area will be bigger compared to the core. Okay, it's due to the fringing. Fringing mean dia kembung dia punya there is like this okay. Okay, this is called a fringing effect. Okay, dia macam ada apa, barrel effect, barrel itulah. Okay, so when there is an air gap, you need to know that the area will be bigger. Okay, how much bigger? Okay, sometimes I think during the exam they will give you for example they say 5% bigger. Okay, 5% bigger or 10% bigger. Okay, so when they say 1% or 5% bigger, so bigger mean that the area of air gap you need to times with, for example, 5%, 5% bigger. So 5% become 1.05 times with the area of the core. Okay, so this is how you calculate. Okay, 5%, there will be 1.05 times with the area of the core. Okay, if 2%, so it become 1.02. Okay, AC, this is AG. Okay, area of the air gap. Okay, so tak perlulah, no need for me to explain how from 2% become 1.2%, 1.2 so you boleh tengok balik lah matematik nanti. Okay, so however is the still easiest tool to design, but the result is okay lah, can acceptable lah, let's say. Okay, satisfactory. Okay, example 1. I think we read it first. Okay, a ferromagnetic has a 3 sides of uniform, 3 sides, they say 3, okay, uniform width. Okay, so yeah, as we know that the core, of course, they have a 4 sides. Okay, for example, this 1, 2, 3, 4. So this one they say 3 side uniform. Okay, it might mean that this 1, 2, 3 or 1 for this side. This side. Okay, this side is similar. Okay, the similar pula, the same uniform sama lah. Okay, length dia sama, panjang dia sama, lebar dia pun sama. Bukan, dia kata width dia dia punya lebar tu sama. Okay, they say for example this one 15. Okay, this one also 15. Okay. Okay, so this one 10. Okay, so the width is different. Okay. Okay, and then while the fourth side is slightly thinner. So this side is slightly thinner. Okay. So the depth of the core is 10 cm. So then we need to know lah the depth. Okay, depth is 10. So from the depth we can calculate the area. Okay. The area is not this area. Jangan salah faham. Not this area. Not this area. Okay, bukan area yang kita nampak ni, surface ni, tapi area yang kedalaman dia lah, ke belakang ni. Okay. So this area, kita ambil area kat tepi ni. Seolah-olahnya dia dekat belakang tu lah. Dia tebal macam tu kan. Okay, so kita nak area yang ni. Ni area. Okay. So kita dah ada yang depan ni punya ni, dan kita nak tahu belakang ni berapa jarak dia. So baru kita boleh ada area. Okay, so the number of turn. Okay, so the number of turn of the coil wrapped around the left side of the core are 200. Okay, so n is equal to 200. So assuming the relative permeability. So this is the trick. Okay, relative permeability. This is not mu. This is a mu r. Okay, of the ferromagnetic core is 2500. And then they ask you how much flux will be produced when the current 1 ampere is applied. Okay, so how much flux? So they want you to calculate the flux. Okay, so we can write it first. So the equation so this is equal to BA, and then ingat tak dia punya equation? Okay, mu NIA over LC. Okay, so then we can ataupun secara ringkas adalah F over R. Okay, so since we know there is a some side is uniform and some side is not uniform. Okay, so when there is not uniform, okay, so we need to calculate it separately. Okay, we cannot take the mean path length all together. Okay, because the area is different. Okay, so since we know that there is a two resistance or two different sides. Okay, so we can convert it into the electric circuit. Okay, so we can write it as a like this. We draw it like first. We convert first. Okay, so this is a force, like a voltage, and then the current flow is a flux and resistance. So we know that there is a two different length. Okay, and or the two different sides, side lah. Okay, so the side 1, okay, we write it as a R1 and then the R2. Okay, so we need to calculate. The first thing that we need to calculate is the reluctance. Okay, so we need to calculate the reluctance first. Okay, I think better I show you the step-by-step calculation, because from there I think you will be see clearly. Okay. Okay. This one much more better. So I try to, I prepared in the slide, but I don't want you to get confused. I think by I write it back will be more good. Boleh nampak tak ni?
Nampak.
Ke kecil sangat?
Nampak. Nampak doktor.
Nampak?
Nampak.
So, alamak dia punya ni pula lagi. Sekejap Okay. So, we need to calculate the R1. Okay. So, what is R1? So, R1, we know that we must use the length of that particular site. So, L1 and then mu A1. Okay. So what is the L1? So L1 length. Okay, from here we need to take the center. Don't forget about the center path length. So since we want to take the center, so we can do like this. Kita separatekan macam ni. Okay. So we take it from here first, 30. Okay. The L1 is equal to 30 plus, is it 15 or 7.5? 7.5 plus bawah ni pun dia center kan, bagi 2 je lah, so 7.5. Okay, so dia bersamaan dengan 45 cm. Okay, ingat cm. Okay, however in the calculation they are not using cm, they are using meter. Okay, convert to meter become 0.45 meter. Okay, 0.45 meter. Okay, don't forget meter. And then the mu, so they give you mu r is equal to 2500. So mu, okay, is equal to mu r mu naught. Nampak tak? Saya macam kecil sangat pula saya rasa. Kecil sangat Boleh lah
Boleh.
Okay, so mu is 2000. Okay, and this one is 4 times 7, 4 pi. Okay, so kita tulis je we write it first. Okay, jangan you konon expert nak terus tulis, terus macam power je nak tulis kan. Okay, kita tulis je. And then the area is side ni 10 Okay, lebar ni adalah 10 and then kedalaman dia adalah 10. So 10 times 10 lah. Okay, 10 times 10 area 1 10 cm. I think kita terus tukar ke meter pun baik lah. Okay, 0.1 meter times 0.1 meter, it will be 0.01. Betul tak? 0.01. Okay, 0.01 meter square. Okay, this one is 0.01 meter square. Okay, and then we calculate the result will be 14,324 ampere turn per Weber. Okay, so ini adalah R1. Okay, and then we need to calculate the R2. Okay, I think try to change the color. Okay, the R2 is equal to L2 mu A2. Okay, so what is L2? Okay, L2 is, of course, mula-mula ni, firstly we take this 5 cm plus 30 plus 7.5. Okay, this is 7.5 and then 7.5 over here plus 7.5 plus 30 plus 7.5 plus 7.5 plus 30 plus 5. Okay, so you tambah semua sekali lah. Berapa ni? Saya nak you tambah semua. Dapat berapa? Sebab saya dah ada jawapan tapi saya nak you tambah semua. Betul ke tak betul ni? Ada yang kira tak? Please calculate for me.
130 Doktor.
Okay. So 130 cm equal to 1.3 meter. Okay. So 1.3 meter divided by yeah, this one the same because the same core, the same material. Okay, we use the same mu. Okay. So pi. So and then the area is. So this is 15. This is also 15. This is also 15. So area sama lah. So 15 A2 15 0.5 tu 0.15 meter darab 0.1 meter. So will be 0.015 meter square. Okay, 0.015 meter square. Okay, and then you will get 27,587 ampere turn per Weber. Okay, so we have already the R1 and R2, and then we need to add together. So because it's in series, so we need to add it together. R1 plus R2. Okay, it will be 41,911 ampere turn per Weber. Okay, so we have already had the RT. Okay, the R. So now we can calculate the F over R. Oh, not F like this. Silap. The symbol kita kena tulis betul lah. F R. So F is equal to Ni. N is 200. I is 1 ampere. And R is 4199911 per Weber. Okay, and then we will get 0.0048 Weber. So this is the flux. Okay. So until now you can follow. Can you follow?
Yes, okay.
Boleh follow Okay, baik. So then they say, how about we calculate the flux when the N is 300 and the current is 200. Okay. So the difference for the question B is only the turn and the current. Okay. Turn, the number of turn and also the number of current. The amount of current. Okay. The resistance is still the same. Okay, because the same material, same core. You can say B here, so this is A. So B, so same calculation, plus R and I, R, so N is 300, I is 2, and resistance will be same, reactant. Okay, so the answer will be, ini sudah ni tak kira
0.0143
Okay, very good. Okay, so please use 4 decimal places. Okay, please use 4 decimal places. Okay, so I can see from the student previously they use sometimes they didn't use any decimal places, directly take the integer number. Okay, kalau macam ni pandai pula, nanti dia ambil 0.004 sebab 000 belakang tu kan. Okay, sometimes kalau macam ni kan, student buat ada 17.4567 kan, student ambil 17 je, suka-suka dia je nak ambil macam tu. Okay, so jangan so you please use 4 decimal places because your answer will be more accurate. Okay, so macam mana pula kalau dekat 3 C ni? Okay, so about the C, they say calculate the flux density. Okay, flux density mean the B at L1 and L2. Okay, so the only thing the same for the overall here is the flux. Okay, flux tu akan sama. Flux will be the same for the all material, all length. Okay, but the density will be different for each. Okay, so we know that the flux is equal to BA. Okay, so however we can use to measure at a specific at the specific L1 and L2, we must use specific area. Okay, specific place. Okay, for example, B1. Okay, if you want to calculate the B1, we must measure for A1 equal to flux. Okay, this flux also will be the same for B2 and A2. Okay, so please remember sama je semua. Okay, but we separate it first. So B1 equal to flux divided by A1. Okay, so flux we know, I think this one for B for B. Okay, in case of B soalan B okay, flux equal to 0.0143 divided by A1 is what? 0.01. Okay, so this one become 1.4316 T. Okay, Tesla. Okay, this is B1. So B2 flux divided by A2. This one is the same flux, 0.0143 divided by the area 2. Area 2 is this one, 0.015 is equal to 0.9544 Tesla. Okay, boleh nampak tak? Boleh nampak tak semua?
Boleh betul.
Boleh.
Boleh faham So first, saya ulang balik firstly, first thing that you need to do is identify whether the core is uniform for the all sides or not. Okay, once you identify, you need to find the length for the side. Okay, for the side, and then you convert from the magnetic field, magnetic circuit to the electric circuit, so that you can know what is how many resistance. Is it a serial? Is it a series? Is it a parallel? Okay, and then calculate the resistance or reluctance. Calculate the reluctance. Once you calculate the reluctance, you can measure everything. The flux density. Okay, and please make sure that you understand this thing. Okay, so flux is equal to BA. So BA means at a specific place, specific area. Okay, so and then the specific place times the specific area, the same. Okay, will be the same for the flux. Okay, then you can calculate. Okay, boleh faham? Okay, then kita pergi kepada example 2. Macam ni saya nak buat ni. Tak pandai sangat ni, bukan ni. Page 2 kejap okay, kalau nak cepat boleh je, tapi saya nak you faham sebenarnya. Macam ni. Menarik. Okay, ni example yang the second example. Boleh nampak? Kecil sangat ni. Nampak kecil pula. Okay, the second example, a ferromagnetic core with a small air gap. Okay, now consists of the air gap of a 0.05 cm, very small. Okay, and has a mean path length LC. So when they say like this, it means that all is uniform. Okay, all is uniform except the air gap. Okay, the cross section area, relative permeability, and the coil number. So this is the area, this is the mu r, and this is the number of turn. Okay, if the fringing in the air gap increase, so increase the effective cross section area of the air gap by 5%. Okay, this show that the area, the air gap area is 1.05 of I can say the AC, A core. Okay, so I think they give you everything, so we need to measure the reluctance first. Okay, so they say what is the total reluctance of the flux? Okay, what is the total reluctance? Okay, first of all we need to calculate the RC. Okay, which is R core. Okay, you can name it anything you want. You want to name it as a R1, okay, R2, okay, no problem. To make it easy, I just write RC because they use already the LC. They give LC, mean all core is the uniform. Okay, the formula is, what is the formula? Do you remember? Ingat tak? Hello? The formula?
The
LC divide mu AC. Okay. Okay. Thank you. So LC is equal to 40 cm. So 0.4 meter. Okay. So mu is mu r. Ya, ni jangan lupa mu equal to mu r mu naught. Okay. So they say mu naught mu r is 4,000 So 4,000 by 7, okay, time dengan area. Area dia adalah, dia dah bagi dah, okay. So 12. So area macam mana? Area C 12 cm square. How to convert to the meter? Masih ingat lah nak convert meter macam mana ni? cm ke meter?
bagi 1000
Bagi 1000.
sentimeter to meter.
So katakan kita buat calculation sikit darab ni 10 kuasa negatif 2 kan. So since dia square tu, dia kena darab 2 lah. So dia jadi 10 pula 12 darab dengan 10 negatif 4. Okay, 3 meter lah. So 1, 2, 3, 4 daripada 20. Okay, so 0.0012 meter So RC will be 66,315 ampere turn per Weber. Okay, so this is the RC. Okay, and how about the RA gap? Okay, RA gap will be the RA gap mu A air gap. Okay, so LA gap is 0.05. Okay, 0.05 become 0.0005. Okay, so ni jangan salah. So kita kena convert dalam meter. And then mu R, okay, so mu R for air is 1. Okay, mu R for air is 1 and then 4, 5, 7 and 1.05 times dengan 0.0012. Okay, so this one will be 315, 704 ampere per Weber. Okay, so and then they want the RT, RC plus RAG. Okay, then we plus together this one and plus this one, we get the 382 and 98 ampere turn per Weber. Okay, so this is the total reluctance. Okay, we answer already for the A. Okay, and then they say the current required to produce a flux density. The current required to produce flux density of the 0.5 T Tesla in the air gap. So this one they say that the B at the air gap is this one. Okay, so this is a B air gap 0.5 T. Okay, we know that flux is equal to T air gap and A air gap. Okay, so we calculate this one first. Okay, 0.5 and then 1.05, 0.0012. Okay, berapa dapat ni? Cuba calculate sikit. Tolong saya. Berapa dapat? Tak ada orang kira ke?
6.3 makro.
6.3?
6.3 makro.
Ya ke? Okay, ataupun secara ringkas is it the 0.63 mili ya, betul?
Hello?
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 Ya. Ya, siapa di talian tu? Dia hello, dia diam.
Betul.
Okay, so this is a flux and then they want the current. So kita dah tahu flux same for the whole. Okay, the flux is the same for the whole. So then we know that the flux is equal to F over R. Okay, and then I over R. Okay, and what we want is I. Okay, okay, we want the R flux R over N. Okay, R is RT yeah. Okay, this RT. So we know the flux 0.63 milli. The RT is 382098, and then the N is 400. Okay, and then the result is 0.6 ampere. Okay, so ya, ini yang dimaksudkan lah, dia nak carikan current tu dekat air gap tadi tu. Okay, so boleh faham kat sini? Hello?
Boleh.
Okay. So boleh faham So kalau boleh faham, kita ada satu lagi contoh. Okay, contoh yang lagi satu ni semua sangat berguna lah. Okay, sebab masing-masing dia ada dia punya understanding ataupun pemahaman dia yang berbeza-beza lah. Okay. Okay, yang ni sebelum saya jawab, saya nak awak try dulu fikirkan macam mana ni. Okay. Okay. Try tengok dulu soalan ni. Boleh nampak kan? Boleh meh. Kecil lah. Nampak. Okay, try to read and then try to digest what is that they give everything. And try to give me the way or the flow. what we need to do? Firstly, kita kena identify. Okay? Boleh tak? So I did. A simplified DC motor has a mean path length of 50 cm. So we know already the LC. LC 50 cm. And the cross section area is 12 cm square. Okay. The mean path length for the motor for the rotor is 5 cm. So LR is 5 cm. And its cross section area assumed to be 12 cm also. Okay. 12 cm square. AR 12 cm square. Okay. Similar, same like the core. Each air gap, so there is air gap between the rotor and the core. Okay, each air gap is 0.05. So length air gap is 0.05 cm. And the cross section area is, okay, the cross section area they give already is 14 cm square. Okay, so they say the iron core has a relative permeability 2000. Okay, mu R is 2000, number of turn is 200. If the current of the wire to be set is 1 ampere, find the resulting flux density in the air gap. So which means that the B air gap. What is the B air gap? Okay. First thing we need to do is we convert from the magnetic circuit to the electric circuit. So what we have first? Okay. First we have the power source. Okay. And then we have the core. Okay, the reluctance of the core. Okay, which is the RC. Okay, RC. And then the air gap. Okay, the air gap, the first air gap, RAG1. Okay, and then the R rotor. And then the RAG2. Okay. Alamak, tak sambung pula. Boleh lah ni Okay, so we have 4 here. 4 things here Okay. And the RAG, of course, the RAG RAG is equal to RAG1 plus RAG2. Okay, ataupun RA2 RAG1. Okay, kita ambil satu je lah. Okay, so kita daratkan 2 je. Okay, so we calculate first the RC. So RC is equal to the LC. You need to write like this in the exam. Okay, mu R mu naught AC. Okay, and this one is 0.5, and then 2000 4 5 7. The air is 0.0012. Okay, so the result will be 165,786 ampere per Weber. Okay, jangan lupa unit and then the R okay. LR, then mu R mu naught AR. Okay, 0.05 2000 45 0.012. Terbalik ni. Ni sama ni. Ni. Okay, alamak, ini ada silap kat sini. Okay, I'm not sure mana yang tersilap. Ni sama ada dia kat sini. Okay, so ni ada tersilap sikit ni. Okay. Okay, so boleh kira tak ni? Boleh tolong kira kan untuk saya ni? So ada kesilapan sikit saya tulis. Berapa jawapan dia? Ada siapa boleh bantu saya ni? Tu 6, 5, 7, 8. Okay, sama lah. Okay. 8, 6. Okay. Pattern per Weber. Okay. So and then the RG. RAG. Betul sin kita darat 2 kan. So 2 LAG. Mu R mu not AG. Okay, AG ya. Okay. So AG is 0.0005. Ni darat 2 Kita boleh darat 2 terus. 1, 3, 4, 5, 7. And the area is 0.0014 is equal to baru 5 darat 2. Okay, we have 500 568,410 Newton per Weber. Okay, so then we calculate the R total. Okay, RC plus RR plus RAG. Okay, so the result will be 750,775 ampere turn per Weber. So this is the total reluctance. Okay, and then they say that they want the density. So flux density. So before we get the flux density, we must measure the calculate the FR, the flux. Okay, F over R equal to Ni over R. Okay, so this one is 200. Current is 1. 750,775. This one will be 0.2664 milli Weber. Okay, and then the B, right like this first. Okay, B1, A1. Okay, they say they want A gap. Okay, A gap, A gap, A gap. So B A gap is equal to flux minus with A gap. Okay, 0.2664 milli Weber divided with the area. This is the area of the A gap as 0.014. Okay, and the result will be 0.1903 Tesla. Okay, so this is the magnetic flux density at the air gap. Okay, so boleh faham tak sekarang ni apa yang you kena buat, apa yang you kena cari? Until now boleh ikut? Okay tak semua?
Boleh, boleh.
Boleh
Still boleh ikut.
Okay, so I think for now kita take 5 dulu kita ambil 10 minit kita rehat dulu 10 minit sebab saya pun nak pergi tandas sekejap. Okay, we take 10 we continue back 9:46 9:46 kita sambung semula Boleh semua? Boleh tak?
Boleh.
Okay, so kalau nak stay boleh, kalau nak stay dalam Google Meet ni pun boleh, kalau nak keluar dulu pun boleh tapi nanti masuk balik Okay? Okay, thank you. Kita jumpa lepas ni Okay, Assalamualaikum. Okay, okay, bismillah, kita continue So before kita pergi untuk subtopik yang seterusnya, saya just nak make you expose to you some of the design of the core. Okay, so just now we know that the core is just like this. So yang kita tahu core tu macam ni je tadi kan. Okay, and then dia punya coil lah. Okay, yang kita pun dah tengok yang jenis core yang berbeza. Okay, and then kita ada air gap. Okay, ada air gap and then kita pun dah tengok yang ada rotor. Okay, ada air gap. Okay, so if you can see from here, so all of this is in series. Okay, so please don't forget about the design like this. The core is circle. Okay, please don't forget. So the circle, the area can be box, okay, square, okay. Dia punya ni area boleh jadi macam apa? Panggil macam ni Jadi nak lukis ni. So, kalau kita pecahkan kan, kalau ada bulat dia, so there can be like a box, okay, or circle lah, okay. So akan ada berbeza dia akan beritahu je lah macam mana design dia. Boleh faham maksud saya kat sini? Boleh, can you understand what I mean here? Hello? Boleh faham tak? Kalau jenis core yang bulat, okay, the core, circle core, okay, the dimension or the area can be either box or circle. Okay? Boleh faham
Okay. Okay, Doctor.
So then how if like this? Okay. Okay, so ni saya summary je lah, simplify je lah dia punya circle. Okay, how if like this? Okay, how if like this okay, how if like this? Silap, ni sama je. Ni ada air gap, ni ada air gap, ni ada air gap, ni ada air gap, ni ada air gap. Okay, how if like this? And how if this is L1 and this is L1 and then this is L2, this is L3. So dia ada few setting okay. So if you can see from here, this is in series this is in series. Macam mana dia buat ni? Okay, black okay. So this side is in series. Okay, this is in series. And this is also ni parallel lah. Okay, ni dah masuk parallel lah. So this side is in series. Okay. So we need to make it parallel. Okay, so we need to convert this one, this and this So these two okay. You need to parallel it. Okay, you need to calculate like this R equal to R1 plus R2 okay. So then the circle will be like this okay. So we need to make sure that the circuit like this, then we can do everything easily. Okay, so this side okay is coming from this calculation and the exchanging from this. So this side is the same. Okay, same like here. Okay, so I want you to go to the book, okay, the textbook that I share. Go and find the solution or the question and solution for these cases. Okay, for these cases parallel cases and also the circle cases. Okay, because during the exam we will give you either these two the circle or the parallel case. Okay, so because this one we cover in the class. Okay, so we want you to go and find the solution for these cases. Okay, boleh?
Okay, boleh doktor. Boleh dah.
Okay, so jangan cakap abang tak payung lah. Okay, kita dah bagi hint dah dekat untuk test kan. Okay, so slide pun saya dah share kan. Okay, so ni seterusnya lah. Mana ni? Okay. Okay, we continue. So, the magnetic behavior of the ferromagnetic materials. Okay, so we know that the permeability of the ferromagnetic material is very high, up to 6,000 times. The permeability of the free space. Okay. So in the example, the permeability was assumed to be constant regardless of the magnetomotive force applied to the material. Okay, so as I mentioned before, a lot of assumptions are made for the theoretical. Okay, so although permeability is constant in free space, so this most certainly is not true for iron and other ferromagnetic material. Okay, so tak apalah, ini more theory lah. Okay, so this one is the relationship the relationship between the flux and also the magnetomotive force. Okay, so the more the higher the current because this is Fi the Ni, so N is fixed, so I is varies so the higher the current, and then the flux will be increased. Okay, so at the starting point they will increase linearly, you can say like a linear until certain point they will become saturated. Okay, so mean that whatever number of you increase the current, the flux will be remain. Okay, this is due to the saturation. The material is saturated already. Okay, but the problem, the other thing that will be increased is the losses or the heat. Okay, the current, you increase the current, but the other thing is not increased. Okay, so the more the current, the more heat. Okay, the more the heat. Okay, and will be excessive current. Then the current will affect the temperature, and temperature will affect the other things. Okay, so same goes to the intensity. The intensity. Okay, the higher the intensity, the flux density will be increased. Okay, up to the saturation point. Okay, so they will be different from for the different other type of material. So ferromagnetic is the material that consists of the iron inside. Okay, so yeah, some still is more linear, some still is curvy dan sebagainya lah. So the energy losses in ferromagnetic core, so instead of applying DC to winding, what will happen when the AC current is applied to the winding? Okay, so kita just now we study about the current is constant. Okay, so it's like a DC constant. Okay, and then what will happen when the AC current is applied to the winding? Okay, siapa boleh jawab? What will happen? Lambat. Okay?
Nothing happen.
Nak jawab. Okay, so we assume this is the current. Okay, current flow. This is the AC AC current. So it's like a sinusoidal. Okay. Okay, so when there is a current, okay, from zero, okay, we start from zero. When the current is increased, Okay, you see here from the slide, there is a point here when the current is 0, starting at the starting, and the current is 0, and then they reach up to the point, okay, and then they will reduce, the current will be reduced, okay, will reduce back to the 0, okay. When they reduce back to 0, so then they will reduce again, so they reduce to 0, but the flux is not back to 0, okay. Okay, you can see this is the, jangan dia tak ada relate the current, the graph here is not relate directly to the below graph. Okay, the increase reach to this point, okay, dia dah reach this point lah kan. Okay, and then when they reduce, the current reduce to 0 again, to 0, so the flux will also reduce, but the flux, when the current 0, okay, when the current becomes 0, the flux is not 0. Okay, and then the current keep decreasing, negative, to the negative side, so they will keep decrease. Okay, so keep decrease until the maximum here, and then they will increase again. They increase until 0. Okay, 0 here. So 0, when the current 0, the flux is not at the 0. Okay, okay, then they reach again to the maximum. Okay, so they always like this okay, only at the beginning, only at the beginning the flux start at the 0. Okay, so once the current is flow sinusoidal, okay, sinusoidal, the flux will not reach 0 again. Okay, why? What is this? This is, they call this why. This phenomena is called a hysteresis loop. Okay, hysteresis loop. Okay, so the amount of flux not only depend, okay, but the amount of flux, okay, the flux here not only depend on the amount of the current applied to the winding, but also on the previous history of the flux. So which means that the inherent, okay, the inherent flux inside the material, okay. But they say also previous history of the flux in the core, and this is called a hysteresis. Okay, so dia macam ada remaining punya flux, okay, remaining flux yang tertinggal lah dalam tu, walaupun dia kosong tapi dia masih ada lagi amount of flux dalam tu. Okay, boleh faham benda ni?
Boleh tak?
Soalan, why does hysteresis occur? Okay, so I want you to go to the book, textbook, and find the answer. Okay, kalau saya tanya seorang pun pening ke ni, nanti tak dapat jawab ni. Okay, then the Faraday's law. Okay, so as I mentioned before, so when there is a flux passes through a coil, the voltage will be induced in the turn of wire that directly proportional to the rate of change. Okay, so boleh tengok video dekat sini so bila ada flux, okay, passes through the turn, the voltage will be induced. Okay, so this is the equation. Okay, the induced current equal to negative rate of change of the flux. Okay, okay, what happen when there is a few number of turns? Okay, so you just add the n, you multiply the n inside in front of the d theta over dt. Okay, so why negative is appear in the equation? Okay, this call is Lenz's law. Lenz's law, because of the Lenz's law. Lenz's law mean that we want to the direction of the flux. Okay, the direction of the voltage built up in the coil is such as that if the coil ends where the short circuited, it will produce current. So maksudnya when there is a short circuit, maksudnya you ada coil ni, turn ni, you connect to something okay, which mean that the the circuit is complete. Okay, if there is no voltmeter here, only open circuit, so tak ada lah voltage. Okay, when you short circuit or you put something load, so voltmeter something, the voltage will be produced, the current will flow, and that cause the flux opposing to the original flux change. Okay, so maksudnya bila flux tu macam ni, okay, bila flux yang datang tu magnet macam ni kan, so magnet datang macam ni, so yang tadi coil tu dia turn kan, tak ada apa, so bila dia datang, okay, so bila datang dia punya flux tu agak oppose. Okay, dia macam yang flux yang terhasil tu, the induced flux will oppose. Okay, so dia punya direction like this lah. So ni not south. Okay, not jari saya ni menunjukkan dia ke arah, okay, they go that direction, and this one the produced flux will oppose, okay, this direction, and then this one is this direction. Okay, so that's why negative sign over there. Okay, for example like this, so this is the turn and this is the direction of the flux. Okay, flux tu ke atas kan. So bila flux tu ke atas, okay, bila kita pass through satu magnet ada magnet yang tadi not stop kan. So not stop dia keluar dari sini dia keluar sini. Okay, so then the induced dia macam Lenz law cakap tadi, bila kita ada short circuit and then the voltage will build up, the current will pass through. When the current is appear, the current will produce a magnetic field or the flux. Again, the magnetic flux induced will oppose to the ni lah original flux change ni. So dia punya induced flux tu kan, so direction dia ke bawah ni. So bila direction dia ke bawah, when the direction is below, going below, so we can know the direction of current. Okay, so kita guna yang tadi tu, okay, yang thumb tu kan. So bila direction kanan macam ni, okay, so the current will macam mana? Macam ni. Okay, so the current will enter at this point lah. Okay, so bila dia enter this one, so since this is induced, so the current induced and then the current will keluar sini kan. So sini akan positive and then this negative. Okay, boleh nampak So itu dia punya cara dia lah, kita nak tentukan current flow current flow macam mana So bukan bermaksud current tu bila masuk sini and then sini masuk, maksudnya sini dah positif, bukan. Okay, so ini untuk yang Lenz law untuk Faraday's law, Lenz law yang induced voltage. So di mana dia keluar, di situlah dia positif. Okay, dia tak sama not the same like this dia tak sama macam ni Tadi kita tengok kan yang ni ni. Okay, yang ni kita current masuk, bila current masuk di situlah dia positif. Betul. So this is current is supply. Okay, ni current supply. Okay, so this is when current is supply. Kena ingat tu dia macam seolah-olahnya motor dan generator motor dan generator dia mesti ada terbalik kat situ. Okay, so I think ni pun recap saja. Okay. Okay, so there is one difficulty involved in the Faraday's law equation. So you assume the same flux. So yeah, why difficult? Because they assume the same flux present at each turn coil. Okay. So unfortunately the coil, so coil tu kadang-kadang tu dia longgar kan, dia tak rapat sangat. So bila dia tak rapat, then the coil maybe has some air gap, so the flux will be leakage. Okay, will leaking out lah. Okay, so yeah, dia kata kalau you couple tightly, so majority flux will pass through the coil. Okay, and give the valid answer. But leakage is high, If leakage is high, different operation that does not make assumption is needed. Okay. So yeah, this one is for the yeah, sometimes you can see sometimes the negative just ignore. So sometimes the negative just you can ignore sometimes. Okay. And then this equation mean that you have only one coil. Okay. Only one coil. Okay. One coil only lah. Okay. Ni pun dah dua coil lah. Saya tak boleh. Okay. You ada one coil. Macam ni lah senang kata. Okay. You ada one coil. So this is the equation lah. Bila ada magnet tadi tu. Okay. So this is the equation for the only one coil. Okay. So if you have many coil, okay, so you need to measure each coil. Okay, this is one, for example, flux I, flux 1, flux 2, flux 3, flux 4, 3, 4, and this one till n. So you need to measure each. Okay, each. What is the induced voltage is in each coil. Okay, so this is the theory. Okay, so if there is number of coil, dia akan jadi summation lah. Okay, dia akan jadi summation lah. Okay, ni E, for example dia akan E1 and then E2 tambah E3 tambah E4. Okay, so untuk simplify, dia akan E induce summation of E I. Okay, so dia jadi macam ni lah. Okay, so they pun try to simplify and then they name it as a delta ni lah. Dipanggil delta sajalah. Okay, so the delta here they call it as a flux linkage. Okay, they call it as a flux linkage. Okay, and the Faraday's law can be written like this. Okay, actually it's like a summation of the induced voltage in each coil. Okay, and then you need to know about the eddy current. Okay, so go back and open the book and find what is the eddy current. Okay. Okay, so we move to the next subtopic. Move to the next subtopic where there is a production of induced force on the wire. So this is called a motor action. Okay, this is a motor action. Okay. So an electric current in the magnetic field. Okay, electric current in a magnetic field. Okay, so which means that there is a magnetic field and then you supply a current. Okay, when you supply a current, a magnetic force will be appear. Okay, it will face a magnetic force. Okay, so they say that the magnetic force is perpendicular to the both direction of the current and the direction of the magnetic field. Nanti kita tengok lah. So the direction of the magnetic force given by the left hand rule. So, kita dah tengok tadi kan, left hand rule. So FBI jangan lupa. Okay, FBI, force, B and current. So this is given. For example, this is memang given lah. Given, I is also given lah. Okay, so bila both ni ada, memang dah ada, so dia akan terhasil. So the force will be induced lah. Okay. So for example, in this case, the direction of the B is inside. Okay, B is inside. Okay, B is inside, and the direction of current is downward. Okay, so then I will go to the right. Okay, so the direction of the force represent the thumb. Okay, so yeah, the length dan sebagainya lah. Okay, so imagine like this. So you are the magnet, and this is the direction of the magnetic force. Okay, magnetic flux. Okay, so direction of magnetic flux. Okay, magnetic flux is to the right, and the current is inside. Okay, to the right, Okay, the current is inside. So the direction of the force will be go to downward. Okay. Okay, so same goes to here lah. Okay, so kalau current tu dia upward, dia akan pergi to the left. And when the current is downward, okay, upward to the left, current hilang. Tiba pula hilang. Okay, so bila current nak upward, go to upward. Okay, upward direction, the force will be to the left, and when the currents go to downward, the force will be to the right. Okay, so harap you boleh faham guna motor action, guna left hand rule use left hand rule. Okay, so this is some calculation when the thing that we want to calculate here is the force. Okay, so yeah, we have a FBI F2 ILB ILB. So I, the L, okay, kita tarik, we look at the L. So L is the length cross product with the B. Okay, so length cross product with the B. So convert the L cross product B is equal to L magnitude of L magnitude of B sin theta. Okay, alright, so become like this. Okay, so F equal to Y L B sin theta. Okay, so for this case, the theta is 90 degree. Okay, this case theta is 90 degree. What is theta? So actually the vector L and B. Okay, so L and B. So L in this direction, B is downward. Dia perpendicular perpendicular. So 90 degree. Okay, so if like this, what is the theta? Okay, siapa boleh jawab? Okay, for this case, what is the theta? So this is L. This is L. The theta is what? What is theta? 30. Betul ke 30?
130.
120? Okay, you kena faham dia punya direction sebenarnya. Macam mana saya nak buat ni? Okay, you boleh nampak dekat saya ni, ada ni. So ini anggap ni L length. Okay, dia punya wire lah kan. And then the B is this direction. Okay, tak kisahlah dia upward ke downward ke, yang penting dia punya angle lah. Okay, so what happen when I rotate this one? I rotate atas ni. Berapa angle dia? Boleh nampak tak? Apa yang saya sedang buat ni?
Tak nampak.
Ayah. Macam mana nak tukar? Okay. So ni, okay, ini ada length ada wire contohlah wire kan. Okay, so dia tegak lah. And then this is the direction of the B either downward ke atas ke, doesn't matter lah yang penting dia perpendicular kan. Okay, and then what happen when I rotate yang atas ni? Okay, I rotate dia. Apa dia punya angle sekarang ni? Katakan I rotate dia 30 degree. Berapa angle sekarang? Hello?
90 degree angle.
Angle dia tetap 90 degree lah. Okay? Sebab yang dia nak adalah ni, angle ni. Okay? Angle ni adalah yang dia nak. Yang theta tu yang ni. Okay? Ni theta. Kalau saya rotate sini tak kisahlah 180 ke apa ke. Okay? Dia tetap perpendicular. Okay? So boleh faham So ini salah. Bukan 30. Dia tetap adalah 90 degree Okay, so 30 adalah beta lah. Okay, so dia ada, nanti saya bagi tahu lah term dia. Okay, and then this one is the induced voltage on the conductor moving. Okay, in a magnetic field. So this is the generator action. Okay, so if a wire with a proper orientation move through a magnetic field, a voltage is induced. So ni kalau dah ada magnetic field, okay, magnetic field dah ada, and then kita ambil wire tu, kita movekan wire tu, okay, and then the voltage will be induced inside the wire. Okay, so this one we use the right hand rule for generator action. Okay, so we have the magnetic field and we know the moving direction, we know already because we move the thing. Okay, and then we must have the vector, the V cross B. Okay, the V cross B. We take our right hand. Okay, this is the basic mathematics. How to know the vector of the cross product. Okay, so for example, my finger is the direction, the V. Okay, and the B is downward. Okay, downward lah. Okay, ni dia ke sana, force ke sana, force pula, direction ke kanan. Okay, and the magnetic field is downward. Okay, so saya pun ni direction ke kanan, and then saya pun ke bawah because the magnetic field ke bawah kan, B is downward. So my thumb is the direction of the vector. Okay, the vector of B cross B. Okay, okay, so kita dah tahu tu dulu, the basic. Okay, so and then kita tengok dia punya voltage lah. So E, the voltage induced is equal to V cross B. Okay, so V cross B, so we know that already. The V cross B will be like this. V sin theta. Okay, and then dot with L. Okay, so this is the basic mathematics. Okay, so it will look like this. L cos theta. Okay, so L is dia punya angle tadi tu lah. So okay, so kita dah tahu direction dia. Okay, so direction of VB is like this, is parallel lah to the L. Okay, parallel to the L. Okay, so if L is move, so then we need to include the angle. Okay, okay, so yeah, cos kosong satu kan, kalau cos kosong, betul tak? Okay, so bila cos kosong maksudnya ni lah, so dia punya VB ni in the same direction with L. Okay, so this one is beta dia kosong lah. Okay, so sama macam tadi lah, ni kan, ni beta 30 sebab dia sengit. So ni beta dia equal to 0. Okay, okay, then VB 90 degree lah. Okay, oh ni theta lah, silap, ni theta ni. Okay, ni theta. Okay, tak kisahlah, saya ada tulis kat sini lah. I think I already mentioned below here what is the angle lah. Okay, so alpha is the angle between V and B. Okay, V and B, V and B. Okay, you can say this one is also theta lah, same like the previous one, and this is beta. Okay, okay, so example okay, a conductor moving wire with a velocity 5 millisecond per second, meter per second to the right. They mentioned already. In the presence of a magnetic field, the flux density is 0.5 Tesla into the page. Okay, so it will be like this, and then moving to the right. Okay, this is B. Okay, and the wire is 1 meter. Okay, L is 1 meter. Okay, and what is the magnitude and polarity of the resulting induced? Okay, so kanan. Okay, so the direction is actually the induced voltage is depend on this one, V cross B. Okay, V cross B. Okay, the current the positive side will be upward. Okay, so V cross B kita masukkan je lah formula dia. And then the mu theta tu kosong because they inline. Okay, L is parallel with the VB. Okay, so we just masukkan semua sekali, we get a VBL. So V is 5, 0.5, 1 meter. Okay, and then we get a 2.5 volt. So positive at the top of the wire. So dia ikut ni Ini adalah dimension lah. Okay, tunjukkan dia ke atas. So ke atas adalah positif. Okay, so ini macam ni kita dah nampak lah, siang dah nampak. Okay, dia downward. So positif ke atas lah, positif kat bawah. Okay, so a conductor is moving 10 meter per second to the right into a magnetic field. The flux density 0.5 out of the page, and the wire is 1 meter. Okay, wire the magnetic polarity. So kita pun dah tengok lah. Okay, so kita just masukkan formula dia tadi, V cross B dot L. So VB sin theta, theta is 90 degree, and then L cos theta, L cos beta, beta is 30, and VBL cos theta. So kita dapat 4.33 and positive at bottom of the wire. Okay, so boleh faham tak until now? Kita dah ada sampai ujung ni lah untuk chapter 1 ni. Okay, so ada apa-apa persoalan? Ada apa-apa persoalan?
Setakat ni tak ada.
Okay, so kalau tak ada, I think kita stop dekat sini lah. So,
Hello, sir.
yes?
Sir,
Yes.
would you upload this scribbled note on auto?
What? Excuse me, I can hear you.
I mean, this scribbled note, like, can we find it on auto?
Yes. Already, I uploaded it. I think last week I uploaded.
No, I'm talking of this one that you scribbled on. Like, this one.
This one?
Yeah.
Okay.
Like, will you also upload this one on auto too?
Already in the author.
That's the real note. I mean, this one that you calculated on and stuff like that.
Oh. Okay. For example, you mean like this, this one?
Yes.
No problem. I can upload it. Okay.
Thank
And
you.
the video also I will upload to YouTube, and then you can watch it anytime you want. Okay. And I really hope that everybody of you go back and open the textbook and go to the exercise. Try to do the exercise. Okay. Just please don't rely 100% to this slide. Please don't. Okay. Please don't do that. Okay. You need to do the exercise. You need to go back and study. Okay. If you rely to this, it's very difficult. Okay. Okay, I think I will end the class today. I think we need to take the attendance. Before that, I stop the recording first. Okay.